We come across many types of collisions between different bodies in our daily lives, like the collision between a bat and ball, and the collision between a striker and coins in a game of carom. In the subatomic world, we find collisions between various subatomic particles. For example, a subatomic particle called a neutrino collides with another subatomic particle, a neutron. The neutron disappears and one finds a proton and an electron as products of this collision. In any collision, the linear momentum of the system is conserved. If we consider one-dimensional collision between two bodies, then from Newton's third law of motion, they experience equal and opposite forces, F12 and F21, on each other, such that F12 is the force on the first body due to the second, and F21 is the force on the second body due to the first, and F12 must be equal to minus F21. From Newton's second law of motion, if delta P1 and delta P2 are changes in momenta of the first and second bodies respectively, then force F12 will be equal to delta P1 by delta T, and force F21 will be equal to delta P2 by delta T. Since F12 is equal to minus F21, this implies that delta P1 by delta T is equal to minus delta P2 by delta T. Therefore, delta P1 is equal to minus delta P2, or delta P1 plus delta P2 is equal to 0. Hence, we can say that the total change in momentum during a collision is 0, or we can say that the total momentum of the system is conserved during collisions. There are three different kinds of collisions: elastic collision, inelastic collision, and completely inelastic collision. In a collision, if both the total momentum P and total kinetic energy Ke of the colliding bodies is conserved, then it is an elastic collision. In such a collision, the bodies move separately after the collision and the loss in kinetic energy delta Ke is 0. This implies that there is no loss in kinetic energy. For example, the collision between subatomic particles is an elastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and not the kinetic energy, and the colliding bodies move separately after the collision, then the collision is called an inelastic collision. There is some loss in kinetic energy of the system during this collision. This implies that delta Ke is not equal to 0. For example, the collision between billiard balls is an inelastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and the total kinetic energy is not conserved, and the bodies stick together after the collision, then it is a perfectly inelastic collision. There is a maximum loss of kinetic energy during this collision. This implies that delta Ke is maximum. For example, the collision between a clay ball and a metallic ball is a perfectly inelastic collision. Consider a head-on collision. That is, one in which the velocities of the bodies before and after the collision are along the same straight line. The mass of the first body is m1 and is moving towards right with velocity u1. The mass of the second body is m2 and is also moving towards the right with velocity u2, such that the two bodies are moving along the same straight line. If u1 is greater than u2, then there will be a collision between the two bodies. Let the collision between the two bodies be elastic, which implies that it is a completely elastic collision. Let the velocity of m1 be v1 and that of m2 be v2, just after the elastic collision. Since the momentum is conserved, we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. On rearranging the terms and simplifying, we get m1 into u1 minus v1 is equal to m2 into v2 minus u2. Let this be equation 1. Since the total kinetic energy is also conserved in an elastic collision, we have half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square, or m1 u1 square plus m2 u2 square is equal to m1 v1 square plus m2 v2 square. On rearranging the terms and simplifying, we get m1 into u1 square minus v1 square is equal to m2 into v2 square minus u2 square. On further simplifying, we get m1 into u1 minus v1 into u1 plus v1 equal to m2 into v2 minus u2 into u2 plus v2. Let this be equation 2. Now, dividing equation 2 by equation 1 and simplifying. We get u1 plus v1 minus u2 is equal to v2. Let this be equation 3. Substituting value of v2 from equation 3 in equation 1 and simplifying as shown. We get final velocity of m1 as v1 is equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. Let this be equation 4. From equation 3, we get v1 is equal to v2 plus u2 minus u1. Let this be equation 5. Substituting the value of v1 from equation 5 in equation 1 and simplifying as shown, We get final velocity of m2 as v2 is equal to m2 minus m1 by m2 plus m1 into u2 plus 2m1 by m2 plus m1 into u1. Let this be equation 6.